Hi, and welcome to a video where I show you the entire process of making CNC electronics from start to finish, with an explanation of the electronics at the end of the video. If you are interested in this machine, I will provide a link in the description to the plans so you can make your own. This is a very large 4x8 CNC router. I also offer CNC routers of much larger sizes, and the newest versions of this machine allows the spindle to be repositioned for very long end mills. Okay, back to the CNC electronics. The machine is currently cutting out the base of the electronics and one of the side layers. The way I like to create sides of the electronics is similar to the retro radios, like from the 50s, with curved sides. And I've also seen some really cool subwoofer designs made like this as well. If I design the sides to be really thick, sometimes I use it to hide the wires. I didn't do this in this design, but I think sometimes it's kind of cool to look at the wires, as long as they're neatly routed, in the system. The machine is now cutting out the remaining side layers. If you look closely, you can see the chips are being evacuated relatively efficiently, but chips appear to be locked inside the kerf of the cut until the cut reaches the target depth. It's interesting to see this in fast motion. I'm using a DeWalt shop vac, and man, does that thing suck. There's nothing better than a clean shop. This is how I get the machine to start a new run. Since I'm using material that has some good areas that can still be salvaged, I need to measure these areas and reposition the machine. This is really tedious and really inefficient, but it reduces the waste. I'm not really sure if this is efficient from a cost standpoint, but I would like to hear your viewpoints in the comments below. The machine is finished cutting out the wooden parts. The parts are held in using holding tabs, which are strategic locations where the router does not cut. These tabs need to be cut in order to remove the parts from the sheet of material. I use a multi-tool to do this, and I have a link in the description of the multi-tool that I use. Every 2 minutes of the sped up portion of this video equates to about 1 hour of real time. During the assembly of the electronics, there was a ton of preparation. The design of the enclosure took approximately 3 hours. The recorded time from start to finish was 14 hours, but the actual time was probably more like 20 hours. The price of the electronics to the consumer was $1,700 total, not including the shipping. Subtracting all of the components, the hourly cost was about $20 per hour. It looks like I missed a couple side parts that I needed to cut out. The sides of the enclosure that serve as panels to mount switches, connectors, and terminals is made out of clear cast acrylic at 0.21 inches thick. The top of the enclosure is also made out of this material. Cast acrylic is far better than using extruded acrylic in my experience. The cut sides of the cast acrylic appear soft and frosted, and I love this look. My order of machining operations start with the inside profiles and drills. This way I can use screws to hold down the material while it cuts the outside profiles of the parts. This eliminates me from cleaning up holding tabs for these acrylic parts, as removing holding tabs are a little more difficult, and I find this process easier. Removing holding tabs on the wooden parts, however, is far easier. I use a flush cutting router bit to remove the holding tabs. I clean up the small parts using this device to hold the parts, which keeps a bloody mess off of my table. I'll also include a link where you can get this in the description. This is the first CNC electronics that I include a handle to pick up the whole unit. CNC electronics can be pretty heavy. I am now cleaning up the fuzz on the edge of the wooden parts. This is really easy with MDO, or medium density overlay plywood. I used one of the parts for this, but usually I use just a glove. Most plywood will leave a splintering edge, but this MDO doesn't, and it is a wonderful material to use. To make sure I cut all of the parts out that I need for the enclosure, I am dry positioning the parts. Now that I know all of the parts are made, I can start drilling intersecting holes for the fastening of the acrylic panels. I need to do this now since I won't be able to do this when the unit is assembled. And I can't tell you how many times I've made that mistake. I use a little jig that I made with a drill bushing to clamp around the part and drill through the edges. I designed the enclosure so it won't be too high when the power supplies and drivers are installed by cutting out areas where the power supplies and drivers can be lowered and using acrylic pieces to fasten these devices securely. Nuts I hammered into the base are actually rivet nuts, not standard insert nuts. I find these nuts to be easier to use and will not cause any damage to the wood. They are also less expensive. I will link these in the description. I didn't quite make these areas large enough and needed to sand and file the edges of these areas so the drivers and power supplies fit. This was done off camera. When designing parts for the first time, this is a common occurrence, and many critical design aspects can be overlooked easily. 3 of the 4 drivers and motors used in the system are closed loop, meaning they have a feedback loop that makes sure the motors actually gets to the position intended. The smaller driver you see at the end of the row of drivers is an open loop driver and will move the Z-axis. Now I am installing the USB controller and the 24-volt dual relay board. The controller can control up to 4 axes, X, Y, Z, and A. The relay will be connected to 2 of the 4 outputs that the controller offers. The 24-volt small power supply I just fastened down is used to power the USB controller. Here I am connecting pigtails with spade terminals for the AC connections on the power supplies. These power supplies are switched to 110 volt and I am using 2 separate cables to connect to the main AC circuit. The crimper that I use is so effective that I completely threw out my ratcheting crimper. I'll provide a link in the description. I also use the wire strippers shown in the video and have been using these for a really long time. I've tried other types, but I keep going back to these. After I create the pigtails for the AC connections, I move on to the DC power wires from the power supplies to their respective drivers. There are 2 60-volt power supplies to supply the closed-loop drivers and motors, and one 48-volt power supply for the open-loop driver and motor. Fortunately, the green terminal blocks on the drivers can be removed, so I can easily insert the wires into the terminals and tighten them down. The ends of the wires that are inserted into the green or blue terminal blocks are terminated with wire ferrules. In a much earlier video, I got a comment that putting wires with just stripped ends is not recommended, and the commenter suggested wire ferrules. From that moment, I started using wire ferrules and never looked back. I will also link that in the description. Now I am connecting the USB Mach 3 controller signal terminals to the drivers. This controls the step pulse and direction for each driver and motor. You can see the blue tool that I'm using to crimp the wire ferrules to the ends of the wires. In this system, I am connecting the X-axis signals to 2 of the drivers since the customer's machine has 2 motors for the X-axis. This can also be done with the slave axis, but I'm reserving this axis just in case the customer would like to have a rotating axis in the future. I just finished the X-axis signal wires to the 2 X-axis drivers. Now I am moving on to the Y-axis signal wires to the Y-axis driver. The Y-axis signals took way too long for me to wire. I think I'm going to have to invest in one of those automatic wire ferrule tools. I finally get to the Z-axis signals. I'm going to start working on the motor connectors now. This is the motor connectors panel, and those black little cylindrical things are the motor connectors. I must have forgotten to tighten the power supplies. I am preparing the work table with soldering equipment. The motor connectors have quick disconnect terminal connections on the back, but I've found they don't seem to have a good fit for proper mating terminals. And anyway, it's easier for me to make sure the connections are bulletproof by soldering the connections anyway. I pre-measured cable lengths and soldered them off camera. Now I am putting on larger ferrules on the ends of the wires. Because 3 of the 4 motors and drivers are closed loop, I also need to provide 3 encoder cables. I'm using 6-pin connectors and using shielded cable. I elected to use 2 3-conductor cables rather than 1 6-conductor, as I didn't have any 6-conductor cable in stock. This will give me extra shielding anyway, and these wires are rather close to the motor wires coming off of the same acrylic connector panel. This is probably the worst part of wiring up closed loop motors and drivers, if you want to include a connector on a panel, that is. The wiring isn't difficult, but the stripping, prepping, and soldering of the 2 sides of the connector is very time-consuming. The connector that is fastened to the panel has solder cups, which are little metal cylinders with a little cutout on one side. The stripped end of the wire is inserted in the cup and then soldered. The 22 gauge conductors that I used inserted very easily and posed no difficulty. The other side of the connector, that is soldered to the end of the cable, has a different style of terminal for the wire. These are slightly curved metal terminals with a tiny hole in it. The hole is too small for the 22 gauge wire, so I was only able to solder to the side of the curved metal piece. It was not easy to keep the wire from moving all over the place while soldering. I wouldn't advise soldering a 6-pin connector of this size. On the next build, I will either use pre-made connectors with cables or use larger diameter connectors for easier soldering. I'm going to speed up the rest of this portion because it is boring. Okay, now I am installing the motor connectors on the acrylic panel, but I managed to make the connector cutouts in a mirrored orientation, so I needed to remake this part. Frustrated with this, I moved on to another section of the build, the AC connectors and toggle switches. The toggle switches I am using are typical on-off switches with two leads, where the circuit is either connected or open. I am running the live black wire through this switch. The power connectors I'm using are the same type you would find on the backs of desktop computers, but there's a big difference. These connectors can handle more current, and the provided cables are also rated for higher current. A standard computer cable would most likely heat up and melt and cause a short, so special cables were sourced for this particular system. I love the connections to the toggle switches. They are terminals that use a screw to hold a ring terminal. So all I have to do is crimp on a ring terminal to the ends of the live wires and just screw them in. The AC plug uses quick disconnect terminals, and these are quite secure, so there was no need to solder these connections. The toggle switches are positioned next to the plug that the toggle switch turns on or off. Pretty simple. The entire set of electronics has a max load of 23 amps, so a 30 amp breaker would be needed just for the motion side of the CNC. Since the wires of the AC were not in the form of cables, the wiring was a bit more difficult to make nice and neat. But I was able to do it with a couple of wire ties. These wires would have been nice to hide from view. Now I am wiring up the fan and the 1 amp 24 volt power supply to the AC side. I'm using small wires because the controller doesn't draw much current, and the wires on the fan are already small. I oriented the fan so the air blows into the enclosure to produce a positive air pressure in the enclosure to help keep out dust. If dust becomes a problem, a filter can be added to the small single source of air just below the fan. I just wired the 24 volt power supply to the 24 volt relays and to the controller. Now I am preparing the external terminal strips for the inputs, outputs, relay connections, the 0 to 10 volt PWM signal for the spindle speed, and the available ground and 5 volt connections. There are so many connections to this section of the system that I felt it is more convenient for the customer to wire to terminals rather than trying to wire from a high pin count round connector. This is especially convenient because you can visually see if there are any issues with the connections, and the terminal strips can be used to test continuity where it is very difficult for a typical round connector for this type of testing. You can see where I used larger gauge wires for the relays, since the relays can be used with higher current devices such as routers, shop vacs, and devices for coolant and mist. Each relay is rated up to 250 volts at 10 amps or 125 volts at 15 amps. Of course, you can also use it with DC voltage as well. This part of the process was pretty time consuming, but was very easy to do. This is why you see me doing this on another table. I'm actually wiring this up while watching YouTube videos. It's time to fasten this panel to the base and connect all of the wires to the Mach 3 USB controller. I start by connecting the relay wires to the relay board. As with the other wires, I am adding wire ferrules. You will notice that the wire ferrules have different colors. These colors determine the size of the ferrules. You'll see that I changed the location of the wires on the terminal strip. I think I did this because either the wires wouldn't reach, or I felt the relay wires were too close to the delicate signal wires. I believe it was the latter. Now I am connecting the two outputs that are not going to the relay board to the terminal strip. The two outputs that control the relays are in yellow, which I just wired up. The white wires that I am connecting now are going to the input terminals. These terminals are responsible for the limit switches, home switches, e-stops, and any other signals that you feel that Mach 3 may need to use. These remaining wires are being connected to the spindle speed PWM signal terminals. Finally, I am wiring up the ground wire to several terminals since all of these features require a ground connection. A computer will obviously need to be plugged into the Mach 3 USB controller, so I designed a plate with a cutout for this connection. I am now fastening the first 3 side layers. The top of the enclosure is cast acrylic. This piece contains holes for fastening the sides of the enclosure, vents for the air to escape, and a fly, since the electronics is called the Red Fly CNC Electronics. This is a naming convention that I started back around 2010. Now I am back to the motor connectors. After recutting this acrylic panel a few times off camera, I can add the connectors and install the panel to the enclosure. The connectors that I am adding now are the encoder connectors that I soldered previously. Connectors like this never seem to have enough thread to be fastened securely to a panel of this thickness, which is 0.21 inches. These are typically fastened to metal enclosures that have a very small gauge in thickness. So I needed to prep these holes to allow these connectors to fit. I'm using a zip tie wire combing technique I found on YouTube. Meow. The connections I'm making now are the encoder connections. These closed-loop motors have encoders on the backs of the motors connected to the shaft. The encoders tell the driver the shaft rotation and confirms the shaft is rotating in synchrony with the commanded output by the driver. I'm using the same wire combing technique on the encoder cables and on the step-in direction signal cables as I did with the motor cables to provide some neatness to the cables. The fan is finally being fastened down. I'm not sure why I did this now, because it would have been better to do this when the sides were not installed. Now I'm adjusting the dip switches for each driver. The dip switches control the microstepping and current setting for the driver. I'm taking a moment here to test the voltages for each of the power supplies. Now it's time to wire the motors. The customer required 50 feet of motor cable, so I'm preparing and soldering 50 feet of motor cable to the motors and 50 feet of encoder cable. The encoder cable is shielded since it will be running in parallel with the motor cable. It is advisable to separate them as much as possible, however. You can see that the motors only come with a couple of feet of cable. Each conductor gets a heat shrink tubing to protect the soldered sections from shorting against a neighboring connection. And the overall set of conductors also gets a larger heat shrink tubing. Don't worry, I knew the cat was there. I made sure that he did not get into any harmful situations. A sped up video may look like there's a bit of danger there, but there isn't. Finally, I am finished with all the wiring. I can now complete the assembly of the enclosure. This is where the motors are plugged in. On the bottom, this is the Z-axis motor connector. The next one up is the Y-axis motor connector. It's the motor connector and the encoder connector. The encoder connectors have 6 pins. The next two are for the X-axis or the long axis, and that axis has 2 motors to drive that axis, and it's the 2 motor connectors and the 2 encoder connectors. The motor connector is going to look like this. So the motor connector is inserted. There's a little notch here that matches up with this slot, and then you just twist it to lock it into position. This is the Y-axis encoder connector, and you just match the notch orientation that's on the very top, and you screw in this portion of the connector so it doesn't come out. Now the first of the 2 X-axis motors. And the last of the X-axis motors. Now all of the connectors are connected. On this side of the electronics is where you connect the power cables. You can't use a standard regular type of cable that you'd use for, say, a computer. This has much larger gauge wire inside of it, so you have to use these. You have to use this particular cable that comes with this electronics. Once power is on for these cables, the internal fan will turn on, and the 24-volt power supply and the controller will turn on. And these will turn on the main power supplies for the motors. This system uses Mach 3 to control the CNC electronics. To jog the X-axis, you use the left and right arrows. You can hear the motor spinning when I press those two. The X-axis motor are these 2 motors here, so when I press the left and right buttons, you can see those move. The 3 motors that do use the encoders, they need encoders because they are closed-loop stepper motors. There are 4 total outputs that you can control various devices. Output number 1 and 2 is connected to these 2 relays. When I use the M3 code or the spindle, you'll see that one of the relays is engaged. If I use the M7 code, I have that connected to flood in my Mach 3. You'll see that the other relay also engaged. The way to connect the computer to the controller, you're going to use a USB connector like this, and you're going to plug it into the controller like that. You'll notice that the red LED is blinking, and when you press the reset button in Mach 3, the red LED will stop blinking and will stay on. This will tell you that you have the connection correctly configured for Mach 3, and you're using the correct plugin for Mach 3. In Mach 3, the way I configured the outputs number 1 and number 2 is using config, ports and pins, and going to output signals. The output signals, output number 1 and output number 2, they're both on port 3, which is the port for the controller. And you see I have pin number 1 and pin number 2 here. These are both enabled, and I have them at active low. In the ports and pins, to connect it to the spindle button or the flood button or another button that's on the program run page, you can go to spindle setup. You want to make sure that disable spindle relays is not checked. For me, I put output number 1 for the clockwise and for the counterclockwise rotation for the spindle, because I just want to turn the spindle on. And for the flood and mist control, I have output number 2 for both the mist and the flood. And this is just so I can demonstrate the operation of the relays. These are the various input-output connectors. The relays use these 4 connectors here. These 2 connectors are for relay number 1, and these 2 connectors are for relay number 2. All you need to do is, when the relay engages, these 2 will connect together. And when the relay disengages, this is an open circuit here. So you can wire through an AC electrical device or even a signal level device. Same goes for these 2. The other 2 outputs are these 2 connectors here. The one on top is output number 3, and the one on bottom is output number 4. These 4 connectors here are your inputs. So you can use your inputs with, say, your limit switches or your e-stop or your home switches. These 4 connectors here are ground connectors. So you'll need to use these in conjunction with your inputs and outputs to complete the circuit. These 2 connectors here, the one on the top is the AVI connector. That's the analog voltage connector. The next one here is the ACM, which is the analog common connector. The next one down right here is the 10 volt input for your AVI and ACM to use to control spindle speed. And the next one down is just an extra 5 volt connector, just in case you need 5 volts for something. Since this electronics is relatively heavy, I added a handle that you can use to move this system. To keep the system cool, there's a main fan that's located right here, and there are 2 vents located here, here, and here. So the circulation of the air has to go past the drivers. Each of the large drivers has their own fan, so air can be moving away from the backs of these drivers as well. There are 2 60 volt power supplies and 1 48 volt power supply. The 2 60 volt power supplies are controlling the closed loop stepper motors, and the 48 volt power supply is controlling the Z-axis open loop stepper driver and stepper motor. I hope you enjoyed the video. Please leave a comment, subscribe if you haven't already, and click the like button. Thank you for watching.